In this video, we're going to be looking at the limits of rational functions and how to find them from an algebraic perspective rather than a graphical perspective. In a previous lesson, we looked at the limits of rational functions from a graphical perspective. So if we had the graph of some function that, let's say, looked like this, and this function is going up infinitely far to the right and it's going down infinitely far to the left. Now, positive x values are out in this direction, and as we go further and further on the x-axis, we're approaching positive infinity. Negative x values are out here towards negative infinity. On the y-axis, we know that the function values go up and up and up infinitely far towards positive infinity, and the function values go down infinitely far towards negative infinity on the y-axis, or the function value axis. So what we want to know is, what is this graph doing? So we could say that the limit of this function, let's call it f of x, as x approaches positive infinity is equal to what? In other words, what is the function value doing? As x gets infinitely large, goes out infinitely far to the right, well, this graph is going up infinitely far towards positive infinity. So the limit is positive infinity. Well, likewise, what is the limit of this function, f of x, as x approaches negative infinity? In other words, to the left on the x-axis, the x values are getting infinitely small, while the function is going down infinitely far towards negative infinity. So this is something that we looked at in another lesson from a graphical perspective. Now let's take a look at it from an algebraic perspective. So to do that, first of all, we want to look at three functions. Let's take a look at the limit of x as x approaches positive infinity. Let's take a look at the limit of x squared as x approaches positive infinity, and the limit of x cubed as x approaches positive infinity. Now, what we can do, we can use direct substitution more or less. It's technically, we're not substituting in a number, but let's just, from a conceptual point of view, think about, well, if we substituted positive infinity in for x, then x is getting infinitely large. So the limit is positive infinity. Well, if we substituted this positive infinity in for x squared, just like we do for substitution, direct substitution, we get positive infinity squared, which is also positive infinity. Infinity times infinity is infinity. And here we would do the same thing. We have positive infinity. It's being cubed. Well, that would be positive infinity times positive infinity times positive infinity, which is a really big old positive infinity. So all three of these are reaching positive infinity. They all have the same limit. As the function is approaching, the x value is approaching positive infinity, the function value is approaching positive infinity. But what we're concerned with now is which one is growing faster. Which is growing faster towards positive infinity. And so to do that, let's look at the graph. And so I'm going to move over to Desmos and take a look at these graphs. Here's the graph of y equals x, the first one that we looked at. And we can see that indeed, as the x values are getting infinitely large, the graph is moving up towards positive infinity. And no matter how far we go, it's going to keep going towards positive infinity. Well, the second graph, y equals x squared. As x gets infinitely large, the y values are going up towards positive infinity, but it appears that they're going even faster than x did. So of these two graphs, x and x squared is moving towards positive infinity. In other words, it's going upwards faster than x is. Well, let's take a look now at x cubed. X cubed, as x is moving to the right towards infinity, the graph is also moving up towards positive infinity, which are the conclusions that we reached over here. All three of these were moving towards positive infinity. But which one is moving faster, x or x cubed? Well, clearly x cubed is moving up faster than x is, and it's even moving up faster than x squared is. So x cubed is growing more quickly than either of these other two. The moral of the story here is, and this is important to remember, is the higher the exponent, the greater the exponent, the more quickly that function grows towards infinity. So x squared grows towards infinity faster than x. X cubed grows towards infinity even faster than x squared. Likewise, if I had something like what is the limit of x to the fifth as x approaches positive infinity? Well, it's also going to be positive infinity, but it's going to be growing even faster than the other ones. All right, so why is this important? Well, this is important because we need to know which functions are growing faster than other ones when we have a rational function. So let's just take a look at a simple limit of a rational function. So let's say we have the limit as x approaches positive infinity of x cubed minus x squared all over x minus 2. Well, first of all, if we look at each one of these terms individually, we know that x cubed is going towards infinity. We know that x squared is going towards positive infinity. We just showed that. And so, in the numerator, x cubed is going towards positive infinity, minus this is going towards positive infinity. Now, I'm just ignoring the denominator now. Let's just take a look at the numerator. So we have infinity minus infinity. Well, some people might think that that's equal to 0. Well, infinity minus infinity is not equal to 0. It might be, but in most cases, it's not going to be. Infinity minus infinity will be either plus or minus infinity. And let's take a look at Desmos to see why. So if we go to Desmos, let's just take a look at this function. This function is x cubed minus x squared. So x cubed we know is growing towards infinity. That was this graph. X squared is growing towards infinity. That's this graph. But when we subtract the two, it is still going towards infinity. So the difference of x cubed minus x squared is still positive infinity. So this answer to this is just positive infinity. X cubed minus x squared is positive infinity. But you might be saying, well, how could it be negative infinity? Well, what if we had the limit as x approaches positive infinity of x squared minus x cubed? Well, x squared is going towards infinity and x cubed is going towards infinity. But let's take a look at the graph of x squared minus x cubed. The graph of those would look like this. It's actually going down. So as x gets larger and larger, the y value, the function value, is going towards negative infinity. Negative infinity. Completely different. So x squared minus x cubed is equal to the limit is negative infinity. Well, it's one thing to look at these from a graphical perspective, but how can we look at them from an algebraic perspective? Well, let's go back to this problem. And just looking at the numerator, we know that x cubed is going towards infinity. We know that x squared is going towards infinity. X cubed is going towards infinity faster. We're going to say that it is the dominant term. It is the dominant term. The highest powered term is the dominant term. All right? The highest powered term is the dominant term. So the dominant term equals the highest powered term. So if we have f of x is equal to x to the fifth minus x cubed. The dominant term is x to the fifth. If we have g of x is equal to x to the 21st plus x to the 83rd, the dominant term is x to the 83rd. All right, the dominant term is the highest power term. In essence, the only thing that's really important in a rational function is the dominant term. It is going to overpower all of the other terms. So let's take a look at another rational function. So let's say we have x cubed minus x squared all over x squared plus 2. What we want to do, and this is approaching, x is approaching positive infinity. To find the limit of this, all we need to do is look at the dominant term in the numerator and the denominator. We want to do the dominant term in the numerator and the denominator. So the dominant term in the numerator is x cubed. The dominant term in the denominator is the highest power, or x squared. So I can ignore the rest of this. All I need to do is look at the highest powered term in each, which is the dominant term. So this is going to be the limit as x approaches positive infinity of x cubed over x squared. That's all I need to look at. Now, x cubed over x squared can be simplified. That can be simplified to the limit as x approaches positive infinity of just x, which we know is, by substitution, positive infinity. And there's our answer, positive infinity. So to find the limit of a rational function, we simply look at the dominant term. Let's do one more. Let's say we have the limit as x approaches positive infinity of x squared minus x to the fifth over 2x cubed plus 3x squared. All right, so let's just look at the dominant term in the numerator and denominator. Limit as x approaches positive infinity, that would be this one. Don't forget the minus in front of it. Minus x to the fifth. And down here, it would be 2x cubed. 2x cubed. Well, this then simplifies to the limit as x approaches positive infinity, because these x's can cancel. A negative x squared over 2. All right, so what is the limit of x squared? Well, the limit of x squared is positive infinity, but we have a negative in front of it. Negative positive infinity over 2. So what is a negative times, so think of this as a negative times positive infinity. A negative times a positive is a negative infinity divided by 2. And what's infinity divided by 2? It's negative infinity. So this becomes negative infinity. Kind of squeezing it in there. Negative infinity. Well, what happens if we have something like the limit as x approaches positive infinity of 3x squared plus 2x minus 4 over x squared minus 3x plus 1. Again, all we need to do is look at the dominant term in each. And so we're looking at the limit as x approaches positive infinity of 3x squared over x squared. Well, the x squareds cancel, so this simply becomes the limit as x approaches positive infinity of 3, and the limit of a constant is simply the constant. And so that just becomes 3. And let's do one more with a negative infinity. So if we have the limit as x approaches negative infinity of something like 2 times x squared plus 3x, I didn't need to put that x in parentheses, all over 4x cubed plus 2. Well, again, we only look at the dominant terms. And so that would be the 2x squared over 4x cubed. And the x's cancel out. So this becomes the limit as x approaches negative infinity of, what are we going to have? A 2 over 4x. 2 over 4x. And so what is the limit of 2 over 4x? Well, let's do this by direct substitution. So we're going to have 2 over 4 times a negative infinity. Remember, we're approaching negative infinity. Well, 4 times negative infinity is a negative infinity. So we have 2 over negative infinity. So as the denominator is getting infinitely small, approaching negative infinity, what is this whole thing approaching? Well, remember, as the denominator of something is getting infinitely large or infinitely small, the whole thing here would be approaching 0. And so that is, in a nutshell, limits at infinity.